look at sequence circuits of a star delta transformer. This is yesterday's topic, so I will just revise it for your recollection. That sequence equivalent circuits of a three-phase transformer depend on the connections. We have seen that whether they are primary and secondary connections, it will depend on that, the sequence circuits. Then different combinations can be there. It can be star delta, delta delta, star star, and there are lots of combinations which we'll see. Now, different combinations when we have of these configurations determine different connections will determine basically what they will determine the various configurations of the zero sequence circuits, and also they will determine the phase shift. Okay, it is known that no current will flow in the primary unless the current will flow in the secondary, and the currents will flow in the secondary of the transformer. So we have a small magnetizing current. Last time we have seen we can neglect those currents while we are doing this type of analysis. And then we know when primary current is determined by the secondary current, so both are related by the turn ratios. Also, we have seen that there are 5 combinations, possible combinations are there, 5 to 6 combinations. We'll see 5 combinations normally, and I will be explaining one combination in a detail. Then the rest combination I will just refer, and we'll draw the sequence, zero sequence networks for those. Arrows on the diagrams will indicate the possible paths for the flow of zero sequence currents. Where the zero sequence currents are flowing, that will show the arrows, and absence of arrows will show that absence of arrow is there, that will indicate the transformer connection is such that zero sequence currents they cannot flow. If arrow is not there, that means zero sequence currents cannot flow. So approximate circuits, these are approximate circuits we have seen yesterday also. I talked about why approximate, because we are not including the magnetizing current, and when we are not including that, so that means it's an approximate circuit, it's not an appropriate circuit. Resistance is also neglected. So let's move ahead and we will take the case number 1. Now, case number 1 is, in case 1, we'll be explaining this in the detail. So case 1 is star bank. This is star bank. Both neutrals grounded through impedance. This is the most difficult, that's why I have taken it. Both neutrals grounded through impedance. Okay, so star bank is there. Both neutrals grounded through impedance. Now, let's consider this. We're talking about this figure B. This is figure. Now you can see here, before going to the complete explanation, you can see this is a star connected load this side, and this is a star connected bank on this side. This is the HV side and this is the LV side. Star connected transformer bank with both neutrals grounded through impedance. So neutrals are grounded through impedance Zn. Here neutral is also grounded through impedance Zn. Currents are moving in this direction, currents are moving in this direction in phase A, phase B, phase Z, and this is the neutral. You know, IN is summation of this. IN is also equal to 3Ia0 that we have seen already. So here, similarly here, IB, IA phase is here, IB phase is here, and IC phase is here, and we have currents, neutral current equal to 3Ia0. So this same diagram, we can represent this diagram a pair of magnetically linked winding, because it's on the same core. So we can draw HV side we can draw like this. This is complete VA, up to neutral is VN, then up to here ground is Vn, this voltage is Vn, this is Vn, Va will be equal to Vn plus Vn. So similarly, this will be on the LV side. For the time being, let's talk about this in the detail now. Now this figure which we just discussed, which shows that what it shows the neutrals of YY bank. So we'll talk about the figure B, shows the neutrals of star star bank, okay, that is grounded through impedance Zn on the high voltage side, on the high voltage side. So on the high voltage side, we have shown that neutrals of the YY bank are grounded through impedance Zn. I have seen that on the high voltage side, and Zn on the low voltage side. Okay. So what we have done basically in this diagram, we are grounding it through high voltage side and we are grounding it through low voltage side. This is a high voltage side, this is a low voltage side, and they are connected on the same core through the transformation ratio N1 is to N2. Let's be very clear. The arrow on the diagram shows the direction, show the direction chosen for the currents. So what are the directions for the current? That arrow will show where the currents are going, exactly how the currents are flowing. That's all. So let us say that we will consider this transformer as an ideal. Let the transformers be considered as ideal. Let the transformers be considered as, what are these transformers? Let's say they are the ideal transformers, and later we can add, ideal means that the ratio of the transformation is same, 1:1 on the either side. We have to consider it first for the sake of analysis. Then we can add what we can add. We can add series leakage impedance. Then we'll make a equivalent circuit referred to primary or secondary. We can do that. And later, shunt magnetizing current. If you want it, you can add it. Shunt magnetizing current can also be included if it is necessary. Normally, we don't include these things. So transformer, it is itself considered to be an ideal transformer. It's an ideal transformer. So what's happening to this? We can add a series leakage impedance, and you can also add shunt magnetizing current later on, because that current is very small. Normally we neglect it. So you can add that later on. Okay. Then moving further, for the sake of analysis, what we have to consider, let's consider, let voltage with respect to ground Voltage with respect to ground, we will consider B, VA, VN on high voltage side, and also VA on low voltage side, LV side. You can see here. This is VA here up to from this phase A to ground, it is VA. VNAN is up to this phase to neutral, and VN is from neutral to ground. And similarly, VA is from this phase to ground. So this should be very clear. Okay, so let the voltages with respect to ground be VA, VN, and VA small. Let the voltages with respect to neutral, let the voltages with respect to neutral be, that will be on the high voltage side, that will be VAN, and the low voltage side, that will be V small n. So here what we are doing, these capital letters, how the notations are, sorry, capital letters are assigned for high voltage, side, and lowercase letters are assigned for LV side. So it's very clear. Capital letters are assigned for high voltage side, and lower case letters are assigned for the low voltage side. The windings that are shown, the figure number C, the windings that are shown, rather, the windings that are drawn are drawn in directions parallel directions are those linked magnetically on the same core. Okay, so that means winding we are drawing it. I have shown you already this windings which we are drawn. They are magnetically linked on the same core, and the turn ratio is n is to n1. Okay. The next is the voltage measured with respect to ground on HV side. So that will be given by, so with respect to ground, that will VA is complete voltage. You can see VA that we are considering from the phase A to the ground. So that will be equal to VAN plus VN, as I already told. So VA, voltage measured with respect to ground on HV side, will be equal to VAN plus VN. That is equation number 1. Now substituting the symmetrical components, so we can change this equation to symmetrical components. So it's very clear. I think from here you can see, I have told you this voltage is from phase A to ground. We're considering phase A. Up to here to the neutral point is VAN. Up to neutral point to ground is VN. So this voltage will be sum of these voltages. Very clear in this case. So then Substituting the symmetrical components of each voltage. Substituting the symmetrical components of each voltage. So three voltages are there. We'll consider the symmetrical components. So for first one, it will be VA naught plus VA1 plus VA2 will be VAN. So symmetrical component of this will be VAN naught plus VAN1 plus VAN2, and this voltage we can add. See, you can see plus sign is there because this time the current is going out from the neutral. We'll take a plus sign. When it will be coming into the neutral, we'll take the negative sign. So this sign is 3A0. This voltage here is Vn. Vn is normally equal to, Vn is Zn. Here Vn will be written like this. Vn voltage on the high voltage side will be Zn into In. But we don't want to write that in the In. So Zn into In is already equal to 3Ia naught that we have seen. That neutral current is equal to 3Ia naught. So we'll writing the same thing. So we here will be writing plus 3Zn Ia naught. Just a second. Ia naught. Okay. So next, let's call this equation number second. So what we have done, we have changed this into the symmetrical components of the respective voltages, and only the neutral voltage we know that is equal to 3 multiplied by 0 sequence current. That is 3 into impedance multiplied by 0 sequence current. Now here we can see what we're observing here. Here positive, and you can see from the equation, positive and negative sequence voltages to ground are equal. You can see it. So that means this is positive sequence is equal to the negative sequence. They are same. There is the values will be the same, are equal to positive and negative sequence voltages to neutral. So they are same. That means what? That means VA naught here is equal to VA I naught, VA1 is equal to VAN1, and sorry, not VA naught, VA1 is equal to VAN1, VA2 is equal to VAN2. This is positive and negative sequence, and zero sequence has a different value. Okay. Also, we can say, so positive and negative sequence on the either side of the equation will be the same. So also zero sequence voltage difference between neutral and ground is equal to what? 3Zn into Ia naught. So that means this voltage, difference between zero sequence voltage between neutral and ground, that means neutral on this side, ground on this side, that is equal to this. This is the difference between these two voltages. That means they are not equal. In other words, we can say they are not equal. So on the similar grounds, Similarly, on the low voltage, side we have similarly on the low voltage side we have VA naught plus VA1 plus VA2 is equal to VAN naught plus VAN1 plus VAN2 minus 3Z IA naught. Okay. So similarly, we'll write VA for this on the low voltage side. We'll be writing this value 3 VA naught, VA1, VA2, VAN naught, VAN1, VAN2 minus 3 IA naught. Okay. Now here, why we are writing the negative sign? Negative sign in the equation is because why is negative sign in the equation is because the direction, because we have taken this direction here we can see that is coming out of the neutral. This is positive, so this is going to the neutral, that should be taken negative. So if one is positive, another is neutral. That is just a notation what we have been taking, because the direction IA naught is out of the transformer and into the lines. On the low voltage side. So that means because direction is on the high voltage side is different and low voltage side is different. Okay. Voltages and currents on both sides. So this is about the low voltage side. Similar what we have done, only the difference is that we have taken 3Z I naught because that's the voltage there on the low voltage side for the 0 seconds. Current will be flowing. So that has to be taken negative because other side was taken positive. So this will be taken as a negative. Voltages and currents on both sides of the transformer. So voltage and currents on the both sides of transformer are related by turn ratio that we know. That is, if for voltage it is N1, N2, for voltages it is N1, N2, the current it will be different. If voltage is N2 by N1, then current it will be N1. So this is based on the notation what we have. So that let's have this low voltage side. Let's relate them. So this is VA naught plus VAN plus VA2. So this is the voltage on the low voltage side. This is the low voltage on the low voltage side. So basically we are taking this one, VA small a, that will be VAN plus VN in the low voltage side. So now we will relate this voltage because we have got this can be also related. This can be related on the high voltage side. How we can relate this to high voltage side? So we can relate that. So if we have to get this corresponding voltage on the high voltage side, So then voltage ratio, let us take it n by n2. They are related to each other. So I will write here va n naught. So on the other side, I will write this for n2 by n1 va n1. Okay, and this I can relate third. I can relate n2 by n1 va n2. Okay, then I will write the same thing minus 3 Zn. For current, I will be writing n1 by n2, and current will become, instead of lower case, it will become higher case here. I will explain it again. It's a very simple step. Now, low voltage side I have taken. I want to convert them into the values on the high voltage side, because I will relate later on these two values. I need to relate them together. So what I am doing basically, the two voltages on the high voltage side will be related by what? Turn ratio, that I have explained earlier here. They will be related to each other by turn ratio. So voltage VA and naught on low voltage side will be related to VA and, that means higher case, and naught will be n2 by n1. So I will be multiplying by n2 by n1. And similarly here, if it is current, the ratio will be reciprocal that of the voltage. So that will be n1 by n2, and current will become IA capital 0. So this is the way we have to relate it. So for sake of the simplification, let us multiply both sides by n1 by n2. So when I will multiply, this equation, above equation, will become, so let's call it equation number 4th. Okay, so n1, it will become n1 by n2 multiplied by va naught plus va1 plus va2, and this will get cancelled. This will become va n naught. Okay, this will become va n1. This will become va n2, and minus 3Zn. This will become n1 by n2 whole square into Ia naught. Okay, I will add a page. Okay, here we have multiplied by n1 and n2. Now this value we already know. This value, we can substitute this value right now. This value we know. So let's call it equation number 5. Substituting what? Substituting for VAN naught plus VAN1 plus VAN2 from equation. Let's see which equation we have used that. So yeah, that is equation number 2nd. From equation number 2nd, we can substitute the value. So left hand side will become n1 n2 divided by n1 n2 va naught plus va1 plus va2. On the other side, this, instead of this equation, we can write va naught, we can write this complete equation. So we will write this complete equation. So this is equal to va naught plus va1 plus va2, then minus 3Zn Ia naught minus 3Zn small n1 divided by n2 whole square multiplied by I naught. You should clearly see we need this value. Just a second. Okay, we need this value. So this will go on the other side. So VA naught, VA1, VA2 minus this. So that's what we are substituting here. We are substituting this value here. This value, complete value. Okay. Yeah, this should be capital, sorry. So this has to be here, and is capital. So this is kept. We are substituting this value. So it is clear. Let's call it equation number sixth equation. Okay. Let's move further. So by equating the same voltage of same sequence, we can write now equating the voltages of sequence of same sequence can have what we can have. So now n1 divided by n2 into VA1, first positive sequence, VA1 will be equal to, you can very clearly see there is only VA1. So we will equate capital on the high voltage side. Similarly, this is a positive sequence, negative sequence n1 divided by n2 VA2 on the LV side will be equal to VA2. And similarly for the zero sequence, what we have to do, n1 divided by n2 VA naught. Here only it will be a bit, there will be more terms in this case. So VA naught will be first minus what we'll be doing. We'll get I naught capital common. So we will have 3Zn capital plus, minus sign is outside, so it will be plus 3Zn n1 by n2 whole square, that will be multiplied by IA naught. So let's say this set of equations is 7th and this is 8th. Okay. So I have done nothing, but I have equated the voltage of same sequence, positive with positive, negative with negative, zero with zero, zero sequence with zero. This is IA naught here. Okay. Positive and negative sequence equations are exactly the same. There's no difference in, they are same. They are just related by the turn ratio. And if it is PU system, they will also not be, that will be same. Okay. Now about the zero sequence equivalent circuit representing equation 8, representing equation 8, that is drawn in figure C. You can see here, that is a figure C. Yeah, this is drawn here. Why? Because this will be referred to primary side. So this is the impedance on high voltage side. We have to, this is on the low voltage side, and that will be the impedance on the primary side. So this is complete drawn. Only impedance, this impedance has to be added. Rest is referred to the primary side. Okay. So what we are doing, in this circuit, leakage impedance is Z of the transformer is added in series on high voltage side as shown in figure, so that the total impedance So that what will happen, the total impedance to zero sequence current is, total impedance will be written as Z, that is the leakage impedance, plus 3Zn, which we have already got, plus 3N1 by N2 whole square into small zn. That is the total impedance. And we call it referred to HV side. It will be referred to HV side. Okay. So here we know that shunt magnetizing impedance can also be added if it is possible in the figure C. And then important point is, in case of the per unit system, turn ratio becomes unity. Turn ratio becomes unity in PU system. So therefore, N1 by N2 will disappear. That will not remain there. So we can write Z0 will be equal to leakage impedance plus on the high voltage side plus 3Zn. That will be in PU. So this is all about. So what we have concluded here, that positive sequence and negative sequence for the transformer, any transformer bank is going to remain the same. Only the difference will come in the zero sequence networks, where we have to add the value of 3Zn when the star bank is grounded through impedance on the either HV or LV side. If it's on LV side, we have to do it 1. If it's on HV side combination, if it is both sides, I have done it here. So that's the conclusion what we are drawing from here. Okay, so next topic is, this is clear. Anybody has a question in this case? Moomin is there. Moomin? Not there. Okay, Sana?
Yes, sir.
Anybody has a question? You have a question? Any questions?
No, sir.
It's clear or not?
Yes, sir. Clear.
Okay, so let's move to next topic. It's a simple topic. We'll be doing this today also. So next topic is, we will be talking about the power in a terms of symmetrical components. In terms of symmetrical components. Let's see how we can. Transformer will continue with this 6 combinations, 5 combinations or 6 combinations will be there. And let me look how many combinations are there. Yeah, 6 combinations will be in total. So we'll look into this, how we can draw the zero sequence network. So, but basic is the same thing, how we have to evaluate it. This is the same thing. This is the procedure, how we have to do it. Simple procedure. Okay. So next is, we'll be talking about the power in a terms of symmetrical components. If the symmetrical component current and voltage are known, the power is expended in a 3-phase circuit can be computed directly from the components. So if we know the symmetrical components, then we can compute the power directly from the components. So if this is in terms of symmetrical components. Normal 3-phase power, you have done it in the basic electrical and other in terms of machine. You have done that, but we are talking about the symmetrical components. That's why it's important in this case. If the symmetrical components of current and voltages are known, power is always current multiplied by voltage in 3-phase also. So if they are known, then we can easily compute that the power expended in three-phase circuit can be computed directly from the components. So very simple is, if we know the symmetrical components of current, if we know the symmetrical components of voltage, so we can compute the three-phase power very easily. The total complex the total complex power flowing into a three-phase circuit through three lines, A, comma, B, and C are. As three phases, actual we know actual power is real power plus reactive power. Sorry. That is equal to, we can write VA IA conjugate, that you know already, VB IB conjugate plus VC IC conjugate. Okay, let's say this actual power we are getting from here. VA, VB, VC are what? Voltages to reference at the terminals. IBC are the currents flowing into the circuit in the lines. Terminus, that means terminal voltages are these, and then IA, comma IB, and IC are currents flowing into the circuit in three lines. So that's a current flowing in the circuit in three lines. Okay. So next we have a neutral connection may or may not be present. So we are not worried about the neutral connection. Neutral connection in three phase may or may not present. That is not required. May not be present. Neutral connection is if there is impedance in the neutral connection. Now let us say neutral connection is present. First, if we have to evaluate, or if we have to calculate the power, the connection of neutral may be there or may not be there. The requirement is not mandatory, but still we can calculate. But let's say neutral is present. If there is impedance in the neutral connection, let's say there is impedance in the neutral connection, just we have done a case to ground, same we have done before this lecture. Then what will happen? Then the voltages VA, comma VB and VC, sorry, VB, VA, VB and VC must must be voltages from line to ground. That's a neutral to ground is there. So voltages must be treated as voltages voltages to ground, must be treated as voltages from line to ground. That's the phase voltage we are using the word from voltages from line to ground. That is, in other words, we call it phase voltage rather than to neutral. So it is very clear if we have to calculate a three-phase power, neutral or connection may be present or may not be. If impedance is connected to neutral through ground, then the voltages will be treated as phase voltages, or in other words, voltage from line to ground. So here we can write three-phase power if above equation can be written in terms of matrix. So that will be VA, VB, VC, and we can write this IA conjugate, IB conjugate, IC conjugate. So we can write it like this. Now we also know that we can write the transform of this rows become columns. So this equation can be further written as, I can write it like this: VA, VB, VC, and I will put a transpose. Transpose rows will become columns. So rows will become, this row 1 will become column. So this one row is there, it will become one column. And here we have to take transfer of this column, that will become row. So I can write this column transport equal to that this row. This is a mathematics, simple mathematics, nothing. So this will be as usual: IA conjugate, IB conjugate, and IC conjugate. Okay. Okay. So what does here mean conjugates? Conjugates, what's the meaning of conjugates in this case? So conjugate will be, what will be conjugates? Conjugates will be the conjugates of corresponding elements of original matrix. That everybody knows. The matrix is there, you take a conjugate of that. So that will be such a conjugate in this case. Such A is such as A is conjugate of A square. We have seen it. Now what is A? A is 1 at an angle of 120. What is A square? 1 at an angle of 240. We have converted it into the rectangular. It was minus point plus j something here. This was minus point plus j minus. So these are conjugates, sorry. These are what? These are conjugates of each other. We have seen it. Please refer to your lecture number 1 or 2 of this topic. So you can see there A and A square are conjugates of each other. So such as A is conjugate of A square in matrix. In matrix A, we know that matrix A, we have seen what is the value of this, represented in earlier lectures. Okay, I'm writing reference here. We have represented that in earlier lectures. So how I can write? As three phase, I can further write. Now these are the phase values. I can change them to what? I can change them to symmetrical values. What I have to do? I have to multiply this by the matrix A. A multiplied by V naught 1, 2, 3. I will be representing VA, VB, VC matrix by this, by symmetrical component, because I am multiplying that. Phase will be changed by multiplying. You know this already. And transpose will be there. Similarly, we will be doing this also. So this A multiplied by the symmetrical components and take the conjugate of the complete. I hope this step is clear. equation number third. This should be your equation number second. Okay, I'm repeating again. If we have to change the phase values, whether they are voltages and currents, into symmetrical components, we have to just multiply by the matrix A. That will phase voltages will become matrix A into symmetrical components. So that we have seen already in the previous lectures. That notation here for the symmetrical components will be 0, 1, 2, 3, 0 seconds, positive, negative. Similarly for the current. So I will be writing here where V10 will be equal to what? That will be equal to VA0, VA1 and VA2. And similarly, I012 will be IA0, IA1, IA2. Okay, this is clear. It's nothing new in this case. Now for the mathematics, because engineering is based on the mathematics, there is a rule of matrix. Rule of matrix is what? One of the rule, will be applying that rule. Maybe you have forgotten that rule and that's not in your mind because you can't remember everything. Everybody knows that. So rule of matrix states what it states, that transpose of product of two matrices is equal to what? So we have transpose of product of two matrices. See term number one here. See here where I'm pointing my cursor. So this is a transpose. Total transport is there, but it's a product of matrix A and symmetrical components of the voltage. So the rule of matrix states that transpose of product of two matrices is equal to, it's equal to product of independent matrix in reverse order. So product of independent matrix in reverse order. So we'll see that what is. That means the rule says if A V1012 transpose will be written as product of independent matrices in reverse order. So that will be V12 transpose multiplied by A transpose. So that will be product of same matrix with a transpose but in the reverse order. So this you have to remember this rule. So what is that rule? If two matrices we are multiplying and we have a transpose on the top of that, that can be also written as product of the same matrices with the transpose on the top of them but in the reverse order. Okay, so further we can write then using this rule, S3 phase can be written as, so here we can use this. Now we can multiply this V0123 transpose multiplied by A transpose multiplied by A conjugate multiplied by I012 conjugate. So here also it's not a problem. Conjugate is there, so we can take individual conjugates. That's fine in this case. So let's call it equation number 4. Now here we know transpose of A is A. You can check it yourself. Transpose of A is A, and that A and A square are conjugates. That I have already explained. They are conjugates of each other in complex numbers. Hence, so transpose of A is itself A. A is a conjugate of A. A is a conjugate of A square, and A square is a conjugate of A, in other words. So as three phase, we can further write this three phase power. So this we write them VA naught, VA1, VA2, okay, multiplied by A, just a second, yes. So this is transpose. What how we had written this transpose earlier? This was like this. So when we are making transpose of this, that will become row. So it has become row here. See here, this VA naught was in the column. Now it has become row. So we are writing it row. So that's very clear. Number two step. So instead of now we have A transpose that is equal to A. So that we can write simple A matrix is 1 1 1 1 A square A 1 A square. So this is A. Number third is A conjugate. So wherever there is A square, that will change to A, and wherever there is A, that will change to A square. That's the conjugate meaning. So that will be 1 1 1 1 1 A square A square A. So that is conjugate we have applied here. A conjugate means only the values of A square and A are interchanged. Wherever there is A, that has to be, we have to use A square. Wherever there is A square, there has to be used, we have to use A. And then this conjugated itself, we are using IA naught, IA1, IA2, and that is in the column matrix, and we are using it in the column matrix. So let's call this equation as equation number 5. Okay, let's move to the next page. Okay, now after this, we can further, and we also know what we also know that if transpose of matrix A multiplied by matrix A, we can calculate it. So that will be equal to, here we can have, that's basically 1 1 1 1 1. That will be A square A square multiplied by A. We have seen that A now. That is 1 1 1 1 1. That will be A square A. If you multiply them together, you can see. So first row with column, that will be 1. You can check. Now second, this first row with second column, that will be 1 plus A square, that will be 0. Third again 0. So next row with this, that will be 0. Next A1 A cube, and then it will be A cube. That will A cube is 1. You know that. So that will be 1. So in the diagonals, you can say after multiplying this, but use this identity A plus A square as it will be 0. So after using this, so you can say this will become 0 0 0 1 0 0 0 1. Only diagonals will have. So it's a unit matrix, but also multiplied by 3, because this will become 3. So unit matrix into 3 it will become. You can check this. This is not a big calculation using this identity. So finally, we can write three-phase complex power will be equal to 3 VA naught, VA1, VA2 multiplied by this conjugate. That means IA naught, IA1, IA2. That is in conjugate. So actual complex power, if we have to write. So therefore, that we have already written three-phase complex power actual beginning, we have written that is equal to as three phase in actual values I conjugate VB IB conjugate VC IC conjugate. Okay, so if we have to write, that is in as three phase actual in terms of symmetrical components, I naught conjugate, I1 conjugate. So this is in actual values. So in per unit value, we can write it like this. This we are just multiplying here. You can see above equation. This equation number 6, this actual equation number 6, we are multiplying. So S3 phase in per unit. So that will be equal to VA naught plus I naught conjugate plus VA1, IA1, sorry, VA1, IA1 conjugate plus VA2, IA2 conjugate. So that is in per unit, because per unit, under root 3 and 3 will not come into the picture in per unit. So I will write it as per unit because the concept of 3 is not there as per unit. Okay, fine. This is fine now. I hope this is clear. Hanji beta. Sana, is it clear or not?
Yes, sir. Clear है.
26. Mansha is there.
Yes, sir.
Is it clear?
Yes, sir.
So that's all for today. We are finished. Next, we'll be doing some more cases of the transformer. 2, 3. Then we'll move to the unsymmetrical faults, where we have line to ground analysis of those faults and the numericals. Okay. Anybody has a question? I'll stop this first. Anybody having a question?